This is the intent of our research efforts. It's a little grandiose, that's the point. The intent of behavioral research is to provide definitive results about causal relationships between behavioral constructs so the results can be broadly applied. Now, when you say that, you're thinking, yeah, that's what I want to do. That's what I want my research to do. There's some variability in whether you're a more focused on theoretical or focused on applied, but nobody minds having the stuff they work so hard on be helpful and useful for people. In academics, there's a couple of standards, one of which is getting your shit into an intro text. There's something magical and special about tens of thousands of intro psych students or comm studies or poly or whatever reading your shit. Don't be embarrassed by that. So here's the thing. There's 4 parts of this that we're going to quarrel about a little bit. We're going to talk about what it means to set these goals. Definitive results, causal relationships, constructs, and broadly applied. Let's take a look. So definitive results, behavioral research. Now, the research we're talking about in here is empirical, quantitative research methods and data analysis. We are limited to that. Once again, I will never say anything negative about qualitative research. I had an opportunity to study with people who were developing this back in the 70s. It was cool. Cresswell and I have an interesting relationship when he was here doing qualitative research, because he would call me up and say, you know, some of your students are coming over here, and I'm pretty sure they don't really want to learn qualitative research. They're just learning how to collect data, and I know they're coding it and putting it in SPSS. I said, yeah, we are. I sent them to you. Thanks. 10 years later, we have mixed methods. That's all I'm going to say. We work very hard to be sure that those data are representative, but they are always incomplete. Remember we talked about representation and inference? That's what we do. That representation is always insufficient, and so our results are never complete. And then we take this incomplete, not perfectly representative data, and we run it through statistical models. The results from the statistical analyses are probabilistic rather than exact. We all know 0.05, but look what... Oh, sorry, let me turn this off. I don't know who you are. Oh, I know who that is, but no. If the null hypothesis were true, that the populations represented by the sample have the same mean DV value, then we would expect to find a statistical value this large or larger less than 5% of the time by chance alone. Thus, we conclude that it is unlikely that populations have the same mean DV value. All of that is captured in P, left pointy, 0.05. We'll talk more about pointies later. That's it. Now, the big word in here for all of this magical stuff, is conclude. We conclude. We do not prove. We conclude. We decide. And when we talk more about p-values, we'll talk more about deciding. Causal relationships. We would love to know what things cause other things. We would love to. It's part of the human condition, and I say that because causal inference is not only through science, but it's through poetry, literature, music. It can be implied by looking at statuary, hieroglyphics. You can't turn around without bumping into people saying, A causes B. I'm just sure. Well, we have to do better than I'm just sure. We have to create methodology that allows other people to be sure that our sureness is right. The evidence you need to say there's a causal relationship, you might as well start memorizing this now. Write it backwards on your forehead. That way you see it every time you brush your teeth. My wife, the dentist, would say, brush often. Temporal precedence. Cause comes before effect. I don't want to have a conversation about particle physics, okay? I had some of that coursework. It's absolutely true. That's not what we're talking about. Statistical relationship. Because if two things aren't related, it's tough for one to cause the other. And then the booger, the absolute pain in the ass. No alternative causes of the effect, no confounds. That when I say A causes B, I have created a situation in which A precedes B, shown that A and B are statistically related, and also created a situation in which there is no D, E, F, or G. That's all. That's all we got to do. The mainstay for this is true experiments, but one of the distinctions that we will make is that a true experiment is defined by process, not result. So running a true experiment in our lexicon is not a guarantee of causal interpretability. We have a whole list of shit that can go wrong. We'll go over it carefully, not today. Random assignment, manipulation controlled by the researcher, and then the magic dot. Systematic control of potential confounds. Just A and B in the world. That's the right face, by the way. That is exactly. She's looking at me like, not with my variables. Absolutely. However, true experiments can't always be performed. Some causes simply can't be randomly assigned and manipulated. I will use the word poofed because it's funny. To poof something means to have absolute control over it in my experimental setting. I can poof number of practices. I can poof which instructions you get. I cannot poof anything about you or your history. Okay, so poof, funny word, drives home the point. Can you really flip a coin and then do what that coin says? Here, you are now a member of this population. Ethics, there's some stuff we can do that we've decided not to. And cost, this is particularly annoying for graduate students. We could, hell, I can approach the equipment that would allow me to do it. And I'm allowed, but I don't have the resources. I don't know if anybody did this intentionally, but one of the great things about graduate school is you learn how to find the second best way of doing things. And you look at a couple of different second and third best and see if they converge. Because if they converge, it not only gives you confidence in them, but it gives you confidence in the best. Very often we discover that the best is only the coolest and not actually the best. Behavioral constructs. Unlike physical attributes often studied in the hard sciences, lots of quotes, mass, velocity, and pressure, most of the attributes we study are constructs. That is, variables that we have made up in order to help organize and explain human behavior. Now let's be honest for a second. I don't know what your exposure to hard sciences is, but most of the hard sciences have given up directly measurable concepts a long time ago. Things are second and third order represented. It started with cloud chambers in the 30s and the 40s. And so this idea that they're magical because they touch all of their variables and we kind of suck because we're making stuff up, is wrong. The purpose of a construct is hopefully to represent, the intent of a variable or a measure or an index or an instrument is to be able to measure a construct well enough that when we measure multiple constructs and look at how they're related to each other, we're learning something useful. That's why later today we will talk about how important attributive hypotheses are. So we want our data to be construct values, but we're limited to variable scores. Often our variables aren't direct, but dependent upon self-report, complex behavioral or content coding schemes. God bless qualitative researchers. The quality of our measures is important. Results can be broadly applied. Come on in. We want our results and conclusions to be meaningful and applicable, either to theory or to practice. But in order to conduct our studies, to get our data, we make choices that can limit the meaningfulness and applicability of the results from the analyses of those data. We're going to talk about methodology as art and craft of science. The reason I call it art and craft is like other arts and other crafts, it's all a bunch of decisions that are made. When an artist or a craftsperson approaches something they're doing, they are constantly making decisions. That's what we do. Those decisions have to be based on knowing the best practices of our research community. Like having read the method section of the last 40 articles, so we know, almost everybody in my group does it this way. Now, you are never going to hear me say not to go to war. about methodology, about measurement, about analysis. What I will strongly encourage is that when you go to war, you know you're going to war, and you know what you're going to war with. We'll tell stories as we go. So the idea is that different combinations of the choices we make, samples, location, tasks, stimuli, manipulations, and measures, can produce different results. If we're going to worry about a replication crisis, we first have to worry about a replicating crisis. Now, here's the cool thing, and this is the first real part of our taxonomy. Every one of these relates to a kind of validity. The validity language is the language you use after you say, I like this study or I don't like this study. When someone says, oh, you don't? Why? Well, no. Anybody. Right? You got to look good after you cast your ballot. Everything you say about the quality of a research study wedges into one of these four. This is the language of quality, language of validity, language of evaluation. So we've got four basic kinds. And this is all you're getting, and I'm sending you off to a pink thing. Because the pink thing is just practice with words, synonym structures. What words herald what? And let me tell you about the pink things. The pink things vary from really well-written, easy to tell what the hell Cal's talking about. I can pick this one, and when I miss it, and you show me the right answer, I do this. Which is okay. There's going to be a lot of this. Oh, wait till we get to SPSS. There are no clever mistakes in SPSS. They're all like, yeah. But some of the pink things are kind of sucky. And those are the ones that I copied out of articles and textbooks. Because we're not really good about writing everything to each other. We're not really good about really being clear. I want you to be better at this, and so I'm going to herd you into it by a combination of really clearly written stuff and stuff that if only it were written this way, it would have been clear. Measurement validity. Do our variables and data accurately represent the behaviors and characteristics we intend to study? This is the one we're going to spend the least time on. But it is arguably the most important, and when you do research to try and figure out why people do and don't read articles, the number one reason that people do and don't read articles is whether they like the way the variables were measured. Who did it, where they did it, how they did it, design, statistical analysis, all of that stuff pales in comparison to, oh, I don't care about the way they measured this. And there's a huge interaction between sort of level of training from first intro stats class to journal editor, several layers in there, and how important measurement is. And the point is that measurement validity is more important to the levels that are evaluating and producing the research. External validity. To what extent can our results be accurately generalized to other participants, situations, and times? That's a good formal definition. Here's mine. What have we learned and how far can we push it? What have we actually sampled? And remember, we're going to have a broader definition of sample than who. Who, what, where, when, and how. Who have we actually learned about? Where are they? Doing what? When? What have we actually learned? And then, how far can we push it? Now, obviously, the how far we can push it part is dependent on our knowledge of the literature and an agreement of how far we're going to push it. Different research communities that snug up against different applications and practice communities have frighteningly different opinions about how far you can push what. Some will not cross the line from animal to non-animal research. Others are pretty much uninterested in the shape or species of where the data came from because that behavior or characteristics pretty important, so much so that we'll generalize across it. That sounds like it's complicated. And always our way of solving complexity is break things down into categories and then take those categories back to our parent literature of our research community. and know what our research community expects. What are best practices? And remember, I'll never tell you don't go to war. Sometimes we have to change shit. Internal validity. The typical definition of internal validity is about causal interpretability. Do we have enough internal validity? Do we have enough control over the situation that we can causally interpret things? Now on Monday, I'm going to change that up a little bit. I want you to worry about internal validity, whether you're testing causal hypotheses or other kinds. Because here's my bold claim. Confounds change results. And confounds change results whether you're going to give those results an associative hypothesis interpretation or a causal hypothesis interpretation. Extra shit floating around in the data changes the data. And variables C, D, E, and F may change the apparent relationship between A and B. That's what the spring is all about. The spring is all about being able to look beyond the relationship between A and B and take C, D, E, and F into account statistically. Right now, we're pretty much dependent on our design to clean stuff up. So we have to be able to look at a design and decide if we think it's clean or not, according to the standards of our research community.
Doesn't measurement validity and internal validity represent the same thing, basically?
Oh, hell no. You can have a really, really good manipulation of number of practices. Okay? I can make absolutely sure these people get 1 and these people get 10 after random assignment. Okay? Now, if I'm not paying attention and the people in the first condition sneak in a couple more, that's a measurement problem. I'm splitting a hair here on purpose. That's a measurement problem. But if the people in this condition want to take longer to reread the instructions and do the task, that's not a property of the measurement of the independent variable. That's a confounding of procedure. You with me?
Okay, so I understand it like measurement is more with, internal validity is more with respect to how am I controlling my experiment.
Yep.
Measurement is how am I measuring my behavior.
That's right. Where do the numbers come from? What's going on while I'm getting the numbers? For example, again, I can stand there and make sure they do it once and they do it 10 times. But if everybody in here is experienced with the task, and everybody here has never seen the task before, that internal validity problem has nothing to do with the measurement. Now, I understand I'm splitting hairs. That's what we do. Okay? So keep asking those questions. Statistical conclusion validity. When it's all said and done, and we have gotten our data, taken our data, analyzed our data, and say, oh, found shit. Are we right? Now, here's one of my favorite slides. I love this slide. Statistical conclusion validity is what we really give a shit, I will claim. We want our results to be right. And here's the thing. As data analysts, as theorists and practitioners, we have a broader definition of statistical conclusion validity and its causes than a straight-up statistician. To a straight-up hardcore statistician who's not working with real data, where they come from and what they represent, but is talking with what the statistical models do as math and as a tool. The fundamental source of statistical conclusion problems is chance, sampling variability, or in the technical language of statisticians, shit happens. But to us, notice the arrows are important. Statistical conclusion validity is driven not only by chance, but by external, internal, and measurement validity. It's not real hard. If you're measuring your variables badly, might you get the wrong results? If you've grabbed a sample that doesn't represent your population, might you get the wrong results? And as I've already said, confounds change results. How we doing? Live this slide. Sir!
We have problems with any of the other three. It's safe to say that we always have problems with them.
That's what I'm claiming. That certainly that's the way we want to think. That's the way we want to set high standards. that to really believe the results that we got, we have to really believe how we measured, how we sampled, how we controlled, and the chances on our side. We'll do more with all of these, I promise. What I'm trying to do today is I'm trying to get you to think about statistics like a data analyst, not like a statistician. And we will see lots of other times where the people who make the tools and the people who use the tools look askance at each other. Yes? There's two choices. Quit and start banging on it. You're absolutely right. When I say we go back to our research community's literature to know what our best practices, we sometimes get back there and go, these don't help. So sometimes you have to slide over. Very often there's some aspect of what is new to us that's not new to somebody else, and you go dig it out. Behavioral scientists are the best or the worst, depending upon how you think about it, at this. Psychologists will borrow from anybody. I'm not going to make any aspersions about the rest of you, but I could. You go and you borrow stuff, you steal stuff, and when you're doing it, you're worried whether bringing it over is a really good idea. But it's something, somewhere to start. And we're going to give you the complete answer to your question in about 12 slides. Yes?
So I'm starting a little bit with how external validity affects inclusion validity.
Sure.
I feel like I get the other two
Okay.
as well. But I feel like, as I've understood external validity, it's how your conclusions can be extrapolated beyond.
Absolutely.
Like,
That's the usual.
So how is it that external validity can affect your statistical conclusion validity as opposed to the other way around?
Gotcha. So here you go. Before I say, and how far can we generalize it? When I talk about external validity, I say, what have we learned? So, you tell me that you want to study third graders. Like, I like third graders. Go study third graders. You don't have enough third graders. So in addition to the 50 third graders, when you promised me 100, you get 25 second graders and 25 fourth graders. Now they're third grade on average. But they're not really the population you went after. And that group might not be representative of the third graders you were claiming all along. The conclusion you get might not really be about third graders, but about mixed grades.
Right. Okay.
That's all I mean. Okay?
Thank you.
Sure. Then you get into fun things like, well, you know, you're looking at a test that's specific to third graders and you gave it to second and fourth graders. What the hell are you doing? Now we've got a measurement problem driven by an external validity failure, and sure as hell that could change things. Remember, all we're talking about here is change that then becomes inaccuracy. When we say, this is who I studied, how, what, where, and when, this is what I found, as long as that description is cool, that's cool. It's when you say, I did third graders with a standardized third grade measure, and you actually did other people. How are we doing? Confounds change results, samplings change results, measures change results. Changed results might not be right.
Like the math speaks to that.
Oh, hell yeah.
But the correct math doesn't matter if the other validity.
Doesn't matter is a little tough because we never really get to do what we want to do, so we're always behind. That's why I say, how far can we push it? Not right or wrong. So this whole wait. All right. If we're trying to acquire knowledge, how do we acquire knowledge? We prefer to acquire knowledge by hypothesis testing. You spend enough time in the literature that you know what other people know, and then based on that, you come up with a hypothesis about what will be the answer when you ask a question that nobody's ever asked before as a graduate student. This is what graduate school is. You know the old joke about you learn more and more about less and less till you know everything about nothing? That's close. But here's the real version. You learn more and more about a more and more specific thing until at the end of 4 years, in that specific thing, you can compete for originality with people that have been doing it for 20 years. Obviously, it's going to narrow your focus. You got 4 years to be competitive with people that have been doing this a lot longer. Hypothesis testing is the way that we do that, the way that we like it. You know this. Okay, 2 attributes of a research hypothesis that I want to emphasize. Has to be testable. We are empirical, quantitative, data analytic types. I got to have data. If I have data, I have to be able to create a situation. And within that, I have to create a testable situation for my hypothesis. And there's those same 3 again. What keeps us from doing this? Insufficient technology, ethics, and resources. Second of all, our research hypotheses have to be falsifiable. We all have that friend who, as an event is approaching, guesses every possible outcome for the event, and then afterwards says, see, I told you. You're not allowed to do that. You got to pick a side. It has to be falsifiable. You have to take the risk of being wrong. A research hypothesis must be testable and it must be falsifiable. 3 kinds of research hypotheses. Here's what I want you to notice. The kinds of hypotheses line up with the kinds of knowledge. Since we do hypothesis testing to acquire knowledge, damn well better. They do. Attributive hypothesis states that behavior exists, can be measured, and can be distinguished from similar other behaviors. It is a one-variable hypothesis. You need to demonstrate a technique that allows a properly trained researcher to reliably record and score the behavior. This is where descriptive knowledge comes from. Associative research hypotheses states that a relationship exists between 2 behaviors. That knowing the amount or kind of one behavior allows you to predict the amount or kind of another behavior. It's a bivariate hypothesis, and the evidence necessary is all 3 words. Reliable statistical relationship. One of the things that you're going to get out of me, and be occasionally annoyed about, is that we got to carry all of the words that matter. Reliable statistical relationship. It's not just a relationship because we're quantitative empiricists. It has to be a statistical relationship. And it can't be once, it has to be reliable. And we will talk about various forms of accruing reliability. P-values, confidence intervals, effect sizes, convergent research, meta-analyses, review, articles, all that stuff. Associative research hypotheses are to build predictive knowledge. Causal states that the differences in the amount or kind of one variable causes, produces, creates, changes, influences differences in the amount or kind of another behavior. It's bivariate, and here we see that again. The evidence needed to support a causal research hypothesis, temporal precedence. The causal variable has to come before the effect variable in the way we collected our data and set up our research. Demonstrate a reliable statistical relationship. What this means is, we'll say this again in a few minutes, no one study is ever truly convincing, even if it tests an a priori literature-based hypothesis and does wonderfully, no one study is ever really believable. This is, some of us whine about, the whole problem with most introductory texts. When you read an introductory text in all of our areas, you get the idea that some real smart person had a really good idea. Then they went out and ran a study and proved that idea, and we're good. Let's go on to the next good idea. It's not how it works. Can't work that way because we don't get things right the first time. So it has to be a reliable statistical relationship to convince a community of analytic, quantitative researchers and practitioners. Elimination of alternative explanations, still the biggest pain in our ass. How clean is this study? Is this study so clean that we've got no other variables floating around changing the results? And confounds can not only screw up causal hypothesis testing, but associative hypothesis testing and even measurement, attributive hypothesis testing. There are ways to set up a data collection so that you get data that don't allow you to decide if that index is reliable and valid. Confounds change results. They change results for all three kinds of hypotheses. They get in the way of acquiring all three kinds of knowledge. We tend to worry about them loudest and most for causal, but we're going to worry about them all the time. We're going to be worriers. So, I want to know if I can predict scores. That's all you need. What kind of hypothesis? What kind of hypothesis? Come on. What kind of hypotheses? Bless you one and all. I want to construct a score that reflects. What do we got? Attributive. I want to know whether I can improve your scores. The other one, causal. Now, there is a hierarchical arrangement among these. Attributive hypotheses are the foundation. If we can't agree how to define and measure things, we can't collect data, and we can't do anything about associative and causal hypotheses. We have to be able to measure stuff. Typically, early in one's career, we borrow the measures of others. If we stay in a research area, we often discover we're unsatisfied with the measures of others, and we go build our own. That has to be done well. Causal hypotheses presuppose associative hypotheses because if two variables are not related, then they can't be causally related. Now, there's a more complicated, more real version of that we will take up when we move into multivariate statistics. Because just because two variables don't share a bivariate relationship doesn't mean that that variable isn't part of the causal and the complex multivariate causal understanding of the outcome variable. But for right now, we're going to go with keeping it simple. If two variables aren't related, we are unlikely to chase learning their causal relationship. Yes?
So in this statement, causation need not be correlation all the time, right?
Say that again.
In the statement of causal hypothesis, a causation need not be a correlation all the time, right?
Right. In fact, we're going to separate the design that gave us the data and the statistical analysis that we used. That's why you won't hear me talk about correlational research or correlational studies. Correlation is most easily thought of as a statistic, and we'll talk carefully about what you have to ask somebody who says, I ran a correlational study, so that you know what the hell they did. One of the things I'm going to constantly be encouraging you to do is ask more questions. Because when people stick a couple of labels on something, they may or may not have told you everything you want to know. And sometimes you have to very politely and gently force our taxonomy onto them so that you can evaluate what they're saying. And the first one we'll run into, someone says they ran a correlational design, you say, thank you. The hell's that mean? Politely. Well, as politely as you need to be. Marvin. Okay. Oh. What have I done? Darn. This isn't the file I intended to upload. What happens if I do this? All right. Okay, I'm going to go somewhere else and grab something else, and we're going to finish talking about this, and then I will get things cleaned up. I'm sorry, I don't know what I did. It worked upstairs.
It might be worth opening it again, though.
Let's try.
The one that I pulled has more.
Well, you know, browsers will give you what's in their cache instead of more slowly going out and looking at the web. Depending upon how you have your same literature that hundreds, thousands, bunches of other people have looked at, you saw a hole in it and found enough information that everyone else has missed to make a guess about what the answer to that new question will be. That is, without a doubt, the coolest. You also we use the research loop for replication. Be sure your conclusions about a particular hypothesis are correct by repeating exactly the same research design. That all your elements of measurement, internal and external validity are the same, giving you a shot at getting the same results. If you run things differently and you find different results, nah. And it is a great way as a young scientist, especially a graduate student, to get positive attention. If a research literature is not finding replication, and you're the one who figures out what they're doing that's not replicating, that's why they're not getting replication, then you run the study to show that you can get both sets of results depending upon how you run the study, you will get positive attention, except by the people who published those two things. So you can only do so much. And then there's convergent research. Convergent research is really tied to that notion of how far can we push it. We're going to decide how far we can push it by running different versions of the study. Different external validity elements, which we haven't talked about yet. Different internal validity elements, which we haven't talked about yet. Different measurement validity elements, same thing. So we look to see what variations of the study give what results. You know, when you run this as a laboratory study, you get the effect. When you run this as a field study, you don't. Or when you run it as a field study more often, I get a bigger effect running it as a non-experimental field study than I do running it as a laboratory experiment. I better figure out how that worked. So there are these three applications of this that are really, really important. Now, just a touch of history and philosophy. If you're even older than me, I know, you might have grown up in a time when the critical experiment was taught. And the notion of the critical experiment comes from physics and chemistry, who have also abandoned it. And the idea of the critical experiment is there's one best way to run a piece of research. And if you run it that way, you find the one best answer. And anything else isn't it? We've abandoned that idea because we know that there's not just one way to run a study, and that sometimes running the study different ways gives different answers. Sometimes we expect it to, other times we don't. But the reason for convergent research is the failure of the critical experiment. What is that one true way to run a study? Now, it's not bad when you're trying to mix oxygen and hydrogen in a lab setting to produce water, and the rate at which you introduce those to each other has an impact on the amount of water. You know, you could talk about better and poorer ways of running that. That's because we know a lot about the chemistry of those two atoms and that molecule. We know a whole lot less about people, animals, societies, groups. And so the idea that we can just sit there and decide, that's the right way to run the study. All others suck it. It's not going to work. We gang up on things. We converge on things. Converging operations. Converging operations is the idea that you keep banging on it until you find one of two things. Consistency or an understanding of what drives inconsistency. I want to make clear. Those are two acceptable outcomes. Running it a bunch of different ways and finding consistent results just means it's easy. But the other acceptable conclusion is running it different ways, getting different results, and figuring out why you get different results. Is it an external validity thing that's going on? Is it an internal validity thing that's going on? Is it a measurement thing that's going on? Or is it chance? All right, I want to tell you a story. What I'm trying to emphasize is that this stuff we've known for a long time. And I can tell you a story. It's not some deeply meaningful research study, and you can identify all the elements. So this is a story about my schoolhouse. I went to an 8-room schoolhouse, not as cool as a 1-room schoolhouse. We had 6 grades and 8 rooms. The other 2 rooms were the cafeteria and the gym. Yes, there were bathrooms. Don't go there. That's not what the crick was for. Down over the hill from the school, there was a crick. Here's the thing. We were allowed to go play in the creek. We would come back after recess drenched in mud, water. Nobody cared. You sat down, you started your social studies reading. It's okay. Nobody had ever jumped that creek without splashing and making a mess. So here's the story. Let's go here. And remember our commitment to not be Blue's Clues. New kid came to school. We showed the kid all 8 rooms. Even showed her the janitor's closet. Walked the kid down the hill into the creek, showed him the creek, showed him the forts that we built, the tree house that we built, and said, nobody's ever jumped the creek. The next day, the kid starts talking to the janitor, other kids, other teachers, parents, finding out, so what's this about the creek?
Library research.
Right? That's what it is. I need to know what other people know before I start doing this. A couple days later, kid walks into gym class and says, I can jump the creek.
Hypothesis for funny.
Oh, can you? Grab the kid, go down the bottom of the hill. And then we decided where the kid was going to stand, how many steps they were allowed to take, where they were allowed to land, and what a splash would be.
Research design.
Research design. Notice what we did. When the kid said, I could jump the creek, we didn't say, oh yeah, give me a competitive argument why you can jump the creek. I want to know if your mom thinks you can jump the creek. We didn't say any of those things. We said, show me. Get your ass down to the creek and let's go get some data. We didn't quite phrase it that way, but we could have. Kid jumps the creek. Little son of a bitch. What is the first thing we said?
Do it again.
Do it again, because we believed, even at the age of 8, in the power of replication. No, we didn't. It just seemed natural. So we did. Jumped it 3 or 4 times. Walk over, jump, walk over, jump, walk over, jump. And now we've got novel research hypothesis, we've got replication, but we're unconvinced. Maybe there's something particularly simple about the set of rules and the location we identified. So, come with me, young child. We're going to go down here to where the weeds are. We're going to go up here to where the sand is. We're going to go over here. We're going to take 2 steps less. Sometimes the kid made it. Sometimes the kid didn't. We were happy as soon as the kid was wet, let's be honest. Data analysis, pretty simple, kid wet or not. Hypothesis testing, over and over. First test, replication, convergence. You know this stuff. All we're going to do is hang language on it. We're going to try and build it into a taxonomy so that you've got a multiple choice test in your head for life. That's all I want. That when you say, all right, I like this study, I need to figure out why, because I'm going to have to tell somebody if I like it or not, because we're all reading this, and the teacher's going to ask somebody in class, and maybe I can be the smart one tomorrow. This is the multiple choice test. Now, I also have for you more of a slide on each of these steps, but I'm not going to read them to you. The point is, and I hope the point's been made, this is not foreign to us. We can argue that earlier is better. Get ready. You're going to hear from me a lot today. You have to know what your research community expects. You have to know from conversations, from going to lab meetings, from reading the literature, particularly the method section, what is expected for the variables, how the variables are measured, and in particular, what are the categories of the variables that are important. We want to make sure that when we're all done with this external validity thing, we've done 3 things. We've gotten 3 bases covered. We have represented our population. We have described that representation to our readers. And then the hardest one, that we obey the boundaries of extrapolation. You need to know what your research community expects in terms of the match between from whom we've collected data, how, where, and when, and what we say we've learned. With the caveat to remember that most of us in the behavioral sciences have for decades tried to get away with grabbing whoever we can and extrapolating to whoever we feel like. There's even a bit about that in the syllabus. That's how much we have wandered on that. All right, so it all starts with research hypotheses. Remember that we have an affection for empirically tested theoretical research hypotheses. What you're expected to learn how to do is to read the same literature that other people have been reading for years, decades, and in there find a hole. Find something, either an interpolation or extrapolation that hasn't been thought of before, and make a guess what you're going to find from that literature. Then, go test it. So it all starts with hypotheses. When we're all done, we have tested those hypotheses, and we want our conclusion to be valid. Valid is just a fancy word for getting it right. Now, here's something else that I'm going to say often. Our job is not p less than 0.05. We'll talk a lot about p less than 0.05 and alternatives and things like that when we get to the second unit. But we typically hypothesize an effect, so we're obviously looking for an effect. But keep in mind, your real job is not to find p less than 0.05. Here comes the harder one. Your job is not really to support your research hypotheses. Or wait a minute, wasn't that the whole thing? Yes, but your real job is to get it right. That means you've got to get a couple of things right. You've got to read the literature properly and generate a good research hypothesis and then support it. Good Lord, it keeps stacking deeper and deeper here, doesn't it? Yeah, welcome. All right. So 4 kinds of validity. The real tough thing about the pink things is that they're all this long. How the hell can I isolate a kind of validity in 40 words or less? It's a pain in the butt. Here's the good news. If you can rip it out of that, let's say, stimulus-poor environment, you're going to do a lot better reading whole articles, listening to presentations, talking with people. Especially when you can say, wait a minute, you what? Why? Because as you understand what they're trying to represent, you understand what kind of representation they're trying to get right. So I know some of them are boogery. Some of them I wrote to be boogery. I will tell you, though, that the worst ones in there were copied word from word, typically from published things. So, measurement validity. We are quantitative empiricists. We get numbers. If those numbers don't represent what we're trying to represent, we're screwed. That's why for many people, measurement validity is the first consideration when they look at a research article. Do I like the way this was measured or manipulated? And if I don't, I may be done with that article. It may go on the B pile. External validity. I like the informal characterization. What have we learned and how far can we push it? Specifically, who, what, where, when, how have we studied? What does that tell us and how far can we push it? And the how far can we push it is strongly tied to the precepts of your research community. There it is again. Internal validity. Internal validity in most treatments are the results causally interpretable? A fine place to start, but remember, and we'll do more on Wednesday and Friday, I want you thinking about internal validity always. Attributive hypotheses, measurement questions, associative hypotheses, causal hypotheses. I always want you worrying about how much is going on in the study that isn't going on in the analysis. That's the hook. What's in the world that's not in the study, what's in the study representing the world that's not in the analysis. Because confounds change results. Confounds change Cronbach alphas and predictive validity coefficients. Confounds change confirmatory and exploratory data factor analyses. Confounds change associations between variables, and confounds absolutely get in the way of causal interpretability. So, two things we're already talking about is an extended meaning of sampling and an extended concern about the quality, the cleanliness, the focus of the variables that we're operating with. And then statistical conclusion validity. When it's all done and we have a conclusion, did we get it right? When we consider the flow of the study, because we care about the flow of the study for two different reasons. When we're designing a study, we have to know what that flow is and when to worry about what kinds of validity. When we're reading about an acquisition of knowledge, a test of a hypothesis, the results of a study, when we're reading about it or listening to it, we've got to know where in the flow we worry about what. This is the color-changing card trick in real life. This is knowing what the changes are going to be and looking for them. So when you're designing the research, you're going to make a whole bunch of choices, and when you're reading the method section, you're reading about all the choices that somebody made, and every one of those choices has an impact on one, the other, or both of internal and external validity. Obviously, when we're collecting data, it's all about measurement validity, except that as we'll talk, as I'm collecting the data, I can reach back and goof up both internal and external validity. We'll talk about there's a lot of language. And when it's all said and done, did we get it right? Now, this is my favorite slide because this slide emphasizes our dependence on much. If our real job is not P less than 0.05, support for the research hypothesis, but to get it right, then there's a whole passel of things we have to get right so we can get the conclusions right. Serious statisticians focus on how statistics behave themselves. And how statistics behave themselves is of particular interest for inferential statistics, where we know we're working from a sample and trying to draw conclusions about a population. And in that bailiwick, chance is a big freaking deal. You don't have to have real data to worry about chance. You're flipping a coin. Is every coin going to land 5 heads and 5 tails? No. That's natural sampling variability. Technical expression, shit happens. But that's part of what we run into. But in addition to chance, statistical conclusion validity, to researchers, practitioners, and applied people, to us, to hypothesis testers, and readers of other people's hypothesis tests, external validity, measurement validity, and internal validity are part of what we're dependent on to have statistical conclusion validity. Keep it simple. If I've got the wrong sample for my population, might I get the wrong answer? If I've got confounds that change results, might I get the wrong answer? And if I'm doing a crap job of measuring or manipulating things, might I get the wrong answer? And, bummer Bob, we can do everything right, and by chance alone, end up with a non-representative and or measurement problem we didn't know about and or confounded study. And this is why we're going to spend so much time talking about replication, convergence. That's why we will end our time together this semester with meta-analysis. Meta-analysis is the really active way of saying not all studies are the same, and not all studies, whether they're the same or different, generate the same results. That's why we do meta-analysis so early in the sequence. It's getting harder and harder to read much without tripping over a meta-analysis, and meta-analyses are increasingly commonly requested as part of a proposal because sample requirement, sample size power analyses are more and more often requested. And if you're going to do a power analysis, the one thing you need is a good estimate of the effect size you're looking for. Where's that going to come from? Probably not. So, this is why we do some of the weird stuff we do in here. Now, while we separate these, and it's useful to look at them separately, it's important to look at them separately. To be honest, sometimes they intertwine and blur and mesh a little. That's not true. They don't really blur, but they intermesh. For example, population and setting. Sometimes where you're studying changes who you're studying. A study of hospitalized patients with schizophrenia versus outpatients with schizophrenia. Definitely a different setting. Probably different schizophrenics. Right? We'd like to think that at least the ones that are at greatest risk to themselves and us are the ones that are inpatients. Right? So just go, don't let reality intercede. This is a perfectly good academic lecture going here. We're just shifting where we're studying, but along the way we're probably changing who we're studying, at least some. Setting in the task stimulus. Where you are may influence what they are doing or the stimulus used. This was a master's thesis that one of the kids did when I was in graduate school. He must have gotten his ass kicked in a bar fight because he spent a couple of years studying how arguments escalate to physical violence. Now, his strategy was that he had people reading these scripted arguments. And the script included when to stand up and pound the table and things like that. And he had galvanic skin response, and he had all sorts of stuff going. And a few of us who had been in bars just always wondered if there might be a difference between not just the setting, but the task stimulus. Is there a difference between how you get riled up reading a script at somebody else who's also wearing a polo shirt than how you get cranked up with 9 beers in you and your friend standing around saying, "Get him!" Okay? Just have to worry sometimes. Where you are may impact aspects of the task and the stimulus. Population and task stimulus. Sometimes you have to adjust tasks and stimuli for who you are studying. And this actually gets awful close to measurement validity problems. A study of elementary versus high school math learning. Different population, probably different math too. It'd be very difficult to think of a math test that would reasonably be given to elementary and high school students at the same time. Make sense? So, while these things blur, that means it's more important to pick the pieces out. Don't just pay attention to, well, clearly they did it in different places. What's the impact of being in different places on who we have, how they're treated, and the rest of it? Another aspect of this that I want you to worry about is a couple of other kinds of validity that have gotten very important and a lot of attention, finally getting a lot of attention. One of them is cultural validity. Different behaviors or relationships between behaviors across cultures. The way I like to handle this within the system is to not expand the system, but to handle it within the system. Most definitions of culture define it by a combination of members and location. In other words, Latinos in New York City aren't the same culture as Latinos in Mexico City. Okay? Where you are and who you are have a combination on this thing we call culture. And this has become very important when people say, well, I'm studying, and they name a group, and what they mean is the 6 of them here at UNL. Okay? That might not be a full cultural representation. Okay, so we got to treat culture as a combination of population and setting elements of external validity. Ecological validity. Anytime anybody uses this word, you got to stop them and ask what they mean, because it means a whole bunch of different things. Because I like history, I want you to know where it came from. Where ecological validity originally came from was in the 60s. In experimental social psychology, they were running a lot of laboratory studies with hardcore manipulations, causal interpretability, very simple stimulus designs, all sorts of cool stuff. And it was boring as shit. So what they wanted to do was to engage the participants, so they put some energy and some thought and some of their personality into it, because that is, after all, what social psychology is trying to study. The social psychological study of bored sophomores. No one ever describes their study that way, though some of them should. And so what they did is they shifted from laboratory settings to real-world mock-ups. They shifted from sitting around a table like this in a room like this to a mocked-up jury decision room. They shifted from reading a transcript to watching a videotape. They shifted from writing out opinions to promulgating arguments among the participants. And that was what was originally meant by ecological validity, getting the study closer to the real-life ecology for the principal purpose of engagement. Along the way, they discovered out that they were increasing their representation, the representativeness. But the original intent was to get folks engaged. One last thing that I want to tie all this to is I want to make the distinction between generalizability and applicability and warn you about one of them. Generalizability means broadly applicable. Broadly applicable. Applicability means application to a specific combination of the elements of external validity. So generalizability is much more demanding, especially in terms of the convergent research required to support claims. If I can replicate a study a couple times that's really been run the same way, then I start arguing easily about applicability. The closer your application is to my population, my setting, my test stimulus, the more applicable my results are going to be. Generalizability goes way beyond replicability and into convergent research. That I've run this on adults and children and old people, and I've run it with real stimuli and constructed stimuli, and I've run it here, there, and everywhere. And it's held up over a 20-year period, which is sort of tough to get done for your thesis. But that's the difference between applicability and generalizability. Generalizability is beyond most of you right now just because you don't have enough content knowledge in your area. Again, that's not an insult. It's a constant reminder, but it's not an insult. So what we'll tend to see on the exam and the story problems is applicability. Here's the way the study was run. Here's a particular thing that I want to apply it to. What's your job? Identify the population in each, the setting in each, the task stimulus in each, and any differences in temporal social. You with me? Okay. The rest of it you'll transition into without even noticing over time. The more you know, the less stupid you'll be. As we'll talk about more next time, or maybe the time after, it's very difficult to have internal validity and external validity at the same time, because control and representativeness do this. And so sometimes you look at a study and you say, this doesn't have good external validity. And so you turn to the author and you say, what the heck? This doesn't have external validity. What are some of the answers you might get? De-emphasizing external validity to emphasize internal validity. If the main focus of the study is causal interpretability, you might make a large number of choices, each of which hinders generalizability. Okay, so somebody basically looks at you and says, I understand that. I did what I had to causally interpret the results. I ran rats instead of children. I ran a passive task because they're very easy to score accurately. I used a lot of shock on the little buggers because it won't really hurt them and it speeds the task and increases the replicability. I know that I'm not telling you about how to treat children in school, but I am learning the relationship between passive tasks and different ways of pushing and modifying them. I'm doing what I want to do, which is internal validity. And that's why we often have applied researchers that go along with every kind of basic research. We even have journals that often have the word applied in them. Now remember, applied doesn't mean specious. Applied means theoretically driven things outside of and beyond finding basic causal relationships. The Applied Journal of Cognitive, or Journal of, I can't remember. It's got applied and cognitive in it. So it's either the Journal of Applied Cognitive Psychology. It's one of the hardest journals to get into. Why? Because it has very high theoretical standards. I don't want you to just apply something. I want you to apply something and learn about it in a real setting. Okay? Tough journal to get into. Great journal to get into. Another approach is to sort of eschew external validity and instead emphasize focused applicability. Basically, the argument is, I ran this study to learn what I needed to learn about. I ran the population that I care about, the setting that I care about, the test stimulus that I care about, and if you care about other combinations, you can run your own damn research. Okay? So, two different common responses to your research isn't externally valid enough. Part of what I'm trying to do is prepare you for when people walk up and tell you these things.
Well, I don't understand what's the point of that. What's the point of studying something if you can't apply it in the real world?
Because if two things aren't causally related in the cleanest of settings, they can't possibly be applied in the real world. And so one approach is to say, what might work there because it works? The other approach is to say, hey, this works, why? Okay? And you see both going on all the time. People are still trying to figure out how the hell aspirin works. The hardcore biochemistry of aspirin is not particularly well known. Not aspirin, aspirin.
No, I said aspirin.
Oh. Well, it's really high and it's got nice trees.
That too.
Those are the causal agents. Okay, aspirin. Okay? So you're right, you see it both ways. But, again, it's that contrast. That causal interpretability comes at a cost of external validity. Sometimes just focused external validity comes at a cost of generalizability. I run into that all the time when I go to conferences and I show people, this is what I've learned about student learning. This is what I've learned about how to use web-based learning. They say, but you're teaching statistics classes. I'd better have a replication with a content course in my back pocket ready to show them, because they will dismiss me because I found it teaching statistics. Okay, so there's an example. And when I pull it into the lab and run the hardcore, strongly manipulated causal experiments, then even if the task stimulus is stats, they will fret. Okay? Fret, fuss, it's hard to know where the line is. Alright, this is the hardest thing we'll do today. Control constants and control variables. They're both controls, so we like them. They help us. They're on our side. A control constant is any behavior or characteristics for which all participants have the same value. One of my favorite tautologies, a constant can't be a confounding variable. A constant isn't a variable, so it can't be a confounding variable. Constants are one of the great simplifying elements of internal validity. Because if something really is a constant, not just because you have shitty standards for equality, but if something really is a constant, it can't be a confounding variable. We'll talk more about this, but I want to mention it now. The flip side is that the more constants you have in your study, whether constants of behavior, characteristic, or process, because you're trying to make sure those are controls, the tougher it might be to generalize from your research. If you tighten down the description of your sample, you are likely to tighten down and limit the generalizability from your sample to a broad population. If you pick a particular task and everybody uses exactly the same task for exactly the same amount of time with exactly the same instructions, all of those things are off the table as confounds, but you now have possibly limited the generalizability of your results. And this is something we're going to have to get used to. Every time we solve a problem, we cause ourselves another one. That's true both methodologically, and I hate to say this, but it's going to be true statistically. Everything you solve by a statistical technique, sometimes trick, cleans up one thing and opens the chasm of others. That's why you will hear me continue to refer to the practice of science as art and craft. Science is the scientific method, but deciding how you're going to exact and engage the scientific method requires scads of decisions among scads of choices. That's what we saddle. That's the saddle, the bridle that we put on. We are going to make those choices for our research, and we are going to evaluate those choices made by others. Now, a control variable. Any behavior or characteristic for which participants have different values. Participants have different values. That's what makes it a variable. What makes it a control variable? But for which the treatment or conditions are balanced or equivalent on that variable. Equivalence doesn't have to be at the person level. If we're comparing conditions, the conditions have to be equivalent. For example, half of the participants are psych majors, half are education majors. Then major is a control variable. It's a variable because we have different kinds. It's a control variable because the two groups are equivalent. They have the same proportional representation. Now you can take just a moment and think about what attrition might do to your study. And it doesn't have to be a 50-50 split. If it's 80-20 here and 80-20 there, it's still an equivalency. The worrying whether the 80-20 is a good idea is an external validity question. Who am I representing with a performance based on 80% of thems and 80% of them and 20% of thems? So who's in the conditions is both an issue of internal and external validity. Who it is external validity. Whether they're equivalent is internal validity. If the participants in each condition have the same average IQ, then IQ is a control variable. So if it's a categorical variable, we're looking for equivalent percentage representation. If it's a quantitative variable, we're typically looking for the same mean. Boy, doesn't it sound like there's a whole lot to talk about? Especially when old Cal stands up here and says the word same, equivalent. What are those standards? You know what I'm going to say. The standards are the standards of your research community unless you think they suck and you want to go to war. So, here's the characterization. We got three kinds of things. Constant, control variables, and confounding variables. In order to completely articulate what the hell's going on, we have to ask two different questions. Are there differences among individual people, and are there differences among groups on average? If everybody's the same, it's a constant. Because if everybody's the same, it can't be a confound. If everybody's the same, the groups can't differ. How close is same? Standards. A control variable is a variable because different people have different values. It's a control variable because the groups have the same on average. A confounding variable is a variable because different people have different values. It's a confounding variable because the groups have different averages or typicalities. And as you might imagine, and might even have come to expect, there's a pink thing. 80% of the treatment group participants have prior experience with the task, and 20% of the control group participants have prior task experience. Is task experience a variable or a constant? Variable. Some do, some don't. That makes it a variable. Are the groups equivalent on prior experience?
No.
So is it a control variable or a confounding variable? Ta-da! Make a little more noise. The secret is nail each thing by itself. Don't start lumping stuff together. Make those intermediate decisions. You will save your ass. That's going to become really important when we get to statistics and hypothesis testing, where you got to take things in stages. You got to nail each thing, make each decision, separate them, or you'll miss stuff. This is all about not missing stuff. 60% of the treatment group participants have prior experience with the task. 60% of the control group participants have prior task experience. Is prior task experience a variable or a constant? If 60% have it, 40% don't. That makes it a variable. Is that variable, where some people have experience and some people don't, Is that a control variable or a confounding variable?
Control variable.
It's a control variable. Control variables are the hardest ones because we tend to equate control with constancy. Control is equivalent variability. None of the participants in either group have prior task experience. Is prior task experience a variable or a constant?
Constant.
So it must be a control. And there's always some dispute about whether we say the word control constant or just say constant, self-actualize. Yeah. So, in the treatment group, 60% have prior experience and 40% don't. So far, so good. Who am I talking to, by the way? Hi. In the control group, 60% have prior task experience, 40% don't. So since some do, some don't, it's a variable. But the nature of that variability is the same in the treatment group and the control group. 60-40 in one, 60-40 in the other. So the proportion of experienced people is the same in both. That gets called a control variable. How are we doing? And so, just to be a whiny professor type, make sure you look at both columns. All participants are 6 years old. Is age a variable or a constant?
Constant.
The way it's expressed here, it looks as a constant. I love that smile. Is that good enough standards? Is year good enough standards?
Depends on the discipline.
Say that louder.
Depends on the discipline or the area. of study.
Research community is the safest word I know. Make sense?
Oh, you could put it depends on the question.
Yes.
There are some 6-year-olds who are cognitively older or younger.
And there's some things that we're studying that we would deeply care and others where we might care less. I mean, if we're talking about a study where the dependent variable is a blood draw and a cell count, we might not need to have it down to the day. Exactly. So, obviously the next two are setups. Okay, I always tell you when it's a trick question. These next two are trick questions. Because in order to answer them, you have to not only be a methodologist and apply the grid for variables and constants and controls and confounds, but you have to know what the standards are for the research. So, the average age of the treatment group is 7, the average age of the control group is 45, and age is not the variable I'm trying to study. Would we consider age likely to be a control or a confound?
Probably a constant.
Confound. I don't know, and I'm a perceptionist, and this is a group of people who cared probably the least of any of us who call ourselves behavioral scientists about defining who was doing the color matching test or who was doing the target detection test. But even among a bunch of perceptionists studying basic orientation phenomena, would probably pull up short if you told us you compared a bunch of 7-year-olds with a bunch of 45-year-olds that had been treated in 2 different ways, and it's the way you treated them that matters. Probably even us. But what about this next one? The average age. I don't know how many times I've looked at that and not remembered to change it. The average age of the treatment group is 7.1 months or years, and the average age of the control group is 7.2. Does that count as a control or a confound? Depends on what you're studying, who you're studying it on, all of that stuff matters. So when we use the magical word constant, we also have to be very careful to articulate what was our equality. How tight do you have to be to say everybody was the same age? Because there are some studies, some kinds of things where that little bit less than a month might matter, especially at that age. Good Lord, am I responsible for what everybody else does? No, just for evaluating it. So here we go. Now my promise to you is I will only split hairs when it is helpful to us. I don't make up extra categories to make things painful. Sometimes it's hard to imagine that. But the reason for having two components of internal validity is that we operate on them differently. The way that we approach controls for the two parts of internal validity are different. Can't back and forth between them. So, initial equivalence. Prior to manipulation of the causal variable, notice when it happens. Before manipulation of the causal variable. Those moments, or days or weeks, but that time in between assignment and manipulation, that's when an initial equivalence either is or is not. Prior to manipulation of the independent variable, participants in the different conditions are the same on average on all measured subject variables. Initial equivalence, measured subject variables. After assignment, before manipulation starts, everybody in the two groups are equivalent on average. Only on average. It doesn't have to be a constant. You can have 80% experience, 20% inexperienced, 80% experience, 20% inexperienced. Balance. Balance is what you need. Equivalence on average. And then ongoing equivalence, which is more annoying than just having a longer definition. Ongoing equivalence is where the art and the craft of the researcher comes into play, where the resources that the researcher has come into play. Because during manipulation of the causal variable, wow, we got right after that. This is like just before that, boom, now we're into ongoing. As soon as you begin manipulating the independent variable, you are now talking about ongoing equivalence. Manipulation of the causal variable. Completion of the task. Remember external validity. Whenever you're collecting data, they're doing something. They're interacting with some stimuli, they're doing some task. During the completion of the task and the measurement of the effect variable, participants in the different conditions are the same on average on all manipulated procedural variables. If you want to, you can add the phrase, except the causal variable, because you are manipulating that. And people differ about how important it is to say that. I'm going to show it to you both ways at different times. We've just covered everything we need to. The conditions are equivalent before we manipulate them. And while we're manipulating them and they're doing their stuff to give us our data, the only difference between them is the causal variable. There was nothing operating before we manipulated. We manipulated one thing. We controlled everything else. At the end of the study, there's only one thing operating on the outcome variable, the causal variable. So if we find a statistical relationship between them, we already have temporal precedence because we manipulated before we measured. We have control over confounds because they were equivalent on average before we started and the whole way through except for the one causal variable. So the only thing left is do the statistical analysis and see if there's a difference between the groups on the outcome variable. Is there a relationship between group membership and the outcome variable? And if there is, hang a causal hypothesis on it. Let's play. Now remember the secret. Initial equivalence is about measured subject variables. Ongoing equivalence is about manipulated procedural variables. Let's talk about this notion of manipulated. Manipulated means it could have been manipulated if the researcher had paid attention and done their job. It doesn't mean they did manipulate it. They might have let it go. Or they might have screwed up. Okay, so manipulated really means manipulatable, but why carry those other letters around? I'm concerned that before the treatment began, there's a hint, before the treatment began, those in the drug treatment group were more depressed than those in the therapy treatment group. So before treatment began is a hint, and we're talking about the depression of the participants. Is that a property of the participants or the procedure? Participants. If it happened before manipulation, and it's a property of the participants, are we talking about initial or ongoing equivalence? That's all there is to it. Slow down. Variable, constant, measured, manipulated. Now start thinking about the role of the variable in a process. Are you sure there's no problem allowing those in the drug treatment group to attend an extra 5 sessions? Those in the therapy treatment group didn't have the extra sessions. Is number of sessions a property of the participant or the procedure? Initial or ongoing? That's all there is to it. The whole next layer of concern and fussing and attention is just an act of will. The vocabulary is not hard. The ideas aren't hard. Doing it every time is what's hard. To save time, there's always some excuse. To save time, only those who were familiar with computers were included in the computer training condition. Everybody else was put in the lecture condition. Is familiarity with computers part of the procedure or part of the participants? Initial or ongoing?
Initial.
How are we doing? Measured or manipulated?
Measure.
Yeah, how are you going to get how familiar you are with a computer? Am I going to impose that on you or am I going to ask? Make sense? Because of the class schedule, those in the computer training condition only had 20 minutes to take the test, while those in the lecture condition had 30 minutes. Now you might say this poor soul, this poor researcher, good heart, had no control. Remember, when we say manipulated, we mean could have been manipulated properly. Is the time of the test a property of the participant or a property of the procedure? So the researcher should have slapped it into account. So, is this an initial equivalence problem or an ongoing equivalence problem?
Ongoing.
The poor researcher might not have had any choice. Okay, awesome, sorry. Still can't have a causal interpretation. So let's look again at an old problem and just use the new language. This is the bilingual 4th graders getting 10 words practiced 5 times on the computer, and the bilingual 2nd graders, 10 words practiced 3 times on paper and pencil. We identified the grade of the school children as a confound. Is grade initial or ongoing equivalence? Wait. Is grade a property of the participant or the procedure?
Participant.
Would it have been measured or manipulated?
Measured.
With those things in mind, initial or ongoing equivalence?
Initial.
Perfect. Number of practices was a confound. Jump, initial or ongoing?
Ongoing.
How you doing? Shit's fun. Because when you say your study's awesome and somebody says, what did you like about it? You now have the language. Well, I like the way you measure things. I like the way you put your sample together. I think the task and the stimulus are awesome. I like the way you controlled this, that, and the other thing. Your initial equivalent's good. That language is the ticket to admission to conversations. When you say, I know my stuff, this is what know your stuff means. That you know the common sense language and you can use it to talk about things. So here's our folks that are part of a study comparing group and individual therapy. We identified number of sessions as a confound, initial or ongoing equivalence. Is the number of sessions a property of the participant when they walk in the door or the procedure as it's carried out? Awesome. And there are some that are really hard, and there's others that you'll get used to, and there will always be a couple that kind of trip you up and you have to stop and think about. I have the distinct advantage. I wrote the story problem. Prior therapy is thy confound, initial or ongoing? Initial, because it's a property of the participant when they walked in the door. Initial equivalence is about things that happen outside the door. Procedural equivalence are things that happen once we begin to manipulate the causal variable. All right. 10 employed patients with no prior therapy completed a 24-session course of group therapy, meeting each time at the University Psychiatric Clinic. 10 other unemployed patients, each of whom had previously received therapy for depression, completed a 10-session series of individual therapy, meeting in a local church. After the respective therapies, the data seemed to support my hypothesis. Initial equivalence confounds. Difference between the participants in the two conditions. How we doing? Okay. I heard all the right grumbles. Ongoing equivalence. Procedural things that were screwed up.
Location,
Location.
the amount of sessions.
Yes. Therapies are IV.
Okay.
I'm sorry. No, backwards. I'm sorry. I screwed these up. I changed this to more. This should be type of therapy. Because the hypothesis, I changed this and forgot to change the answer. Apparently, I don't have an advantage. All right. We've had this conversation before. I wanted to get it on a slide. Traditionally, internal validity is all about causal interpretability. Why? Causal interpretability is about eliminating confounds, so that a statistical relationship between the variables can be properly interpreted as a causal relationship. Why? Because we know that confounds change results. If both the causal variable and the confound are operating, then the results will be changed from what they would be if there was no confound. This generalizes beyond causal hypothesis tests. Confounds change results. They change causally interpretable results, and they change associatively, predictively interpretable results. Confounds change results. If you were to do a large, expensive meta-analysis looking at the replication crisis, and you were to separate the topics that you studied into those that are studied experimentally and those are studied non-experimentally, guess which one shows poorer replication, the experimental or the non-experimental? The non-experimental. Because I'm not running an experiment, I sometimes get a little sloppy with my confound control. I go get the data I can, and I'm depending on cool statistical analysis to give me the right answer. But confounds change results. They change results of causal hypothesis tests and associative hypothesis tests. The better the internal validity, the more accurate the results. Causal results and associative results. And I don't know if I've said this before or not, but let me either start saying it or continue saying it. Our job is not P less than 0.05. We're going to learn about stats. We're going to learn all about P less than 0.05, this kind of error, that kind of error, this kind of right, that kind of right. Look, our job is not P less than 0.05. Now here comes the hard one. Our job is not to support our research hypotheses. Lord, it seems like it, because we work so hard on that literature review and that hypothesis set and the problems and the questions and the hypotheses, and we want to be right. Our real job is to get it right. Statistical conclusion validity, the really important one, which is dependent on internal validity. If we're going to get it right, we have to run a study where the things that are operating are the things that we think are operating. And that's just as true for an associative as for a causal hypothesis test. Yes?
So I just want to make sure I grasp that well. So our job is to...
Good idea. At no point is that more important than considering internal and external validity and how they relate to each other. The argument is every decision that you make has an impact on both internal and external validity. So what's the relationship between them? Historically, there have been two different ways of thinking about how internal and external validity relate to each other. The older one is the precursor model. It comes from a time when the majority of research was laboratory, experimental, causally manipulable results. because the nature of the independent variables or causal variables we were studying was that they were manipulable. And if you can, you should. And that led to the precursor characterization. The precursor characterization is, if I don't have internal validity, if I don't have causal interpretability, I have nothing interesting to generalize. So this argument says the first thing you do is you control anything you have to so you have causal interpretability. And when you're sure you have causal interpretability between that causal and that effect variable, now let it off the chain a little and see if you can make it work in the real world. Okay? Depending upon the kind of research you plan to do, that may make great sense. Other times you look at it and go, I can't even imagine that. I study family type. I study sibling relationships as a causal variable. I'm probably not going to randomly assign and manipulate that ever. So, the trade-off model has become more popular as our presumed causal variables have become more difficult to manipulate, but we still want to think of them as causal variables, so we want to clean things up as well as we can. And as a natural consequence of that, there's more of a mix of associative hypothesis tests and causal hypothesis tests in the same journals that used to be 90% true experiments in causal interpretability, and you never heard if the stuff worked in the real world. You had to go to other journals. The trade-off model says you're going to make a lot of decisions. Everyone has an impact on internal and or external validity, and sometimes you can't have both. Internal validity is all about control. External validity is all about naturalness, representativeness, as close as possible to where it's going to be used. And every decision you make has to be made thoughtfully, worrying about both internal and external validity. See, the precursor model is easy. Stack it up on internal validity and let somebody else worry about the external validity. The trade-off model says, man, there's a lot of ways to run this. What gives me the balance that I need? And because more of our business is done within the trade-off model, and there's more decisions, and there's more variability in their decisions, we're back to worrying about replication as needing to be a process before an evaluation. If you and I make 15 different decisions, and we make a different solution on every one of them, everyone's legitimate and reasonable, what are the chances we're going to find the same simple bivariate relationship between A and B? So, this semester we're going to worry about this. That's about what we're going to do, is we're going to worry. We're going to try and create clean comparisons and comparable comparisons. Next semester, we're going to start looking at statistical models that help us, where we can put into a statistical analysis more than variables A and B. And in addition to all of our hard work to control things procedurally, we can begin to look at how fancier statistical analyses can help clean up the stories we tell. So here we go.
እንግዲህ ወዳጆቼ እንደምታዩት በጣም ብዙ ከሪሰርች ጋር በተያያዘ እንግዲህ እኔ አሁን ይሄንን ሌክቸር አቴንድ እያደረኩ ያለሁት ገና ከመጀመሪያ ዲግሪ እንደመጣ ተማሪ አይደለም። ያቅሜን ያህል ሪሰርች ላይ የተወሰኑ ሪሰርቾች መስራት እድል ነበረኝ። ተማሪዎች አድቫይዝ የማድረግ እድልም ነበረኝ። እኔም አድቫይዘሮች ነበሩኝና አንዳንዴ እንግዲህ ምንድነው በአቅማችን ልክ አንዳንድ ነገሮችን እየሰራን ነን ብለን የምናምናቸው ግን ጠጋ ብለን ስናይ ደግሞ በተሳሳተ መንገድ የሚሰሩ የበለጠ ልናሻሽላቸው የሚገባ ነገሮች ብዙ ነው ያሉትና አሁን በጣም እንደዚህ አጫጭር ቪዲዮ ቲክቶክ ምናምን ከለመደ ወጣት ጋር እንዲህ አይነት ረዘም ያለ እንትን ሰጥቶ ይሄንን ተማር ብሎ ማለት በጣም ከባድ ነው አውቃለሁ። አጫጭር ነገር ለምደናል። ሁሉ ነገር በአጭሩ እንዲያልቅ እንፈልጋለን። ሳይንስ ግን እንደዛ አይደለም ብሎ እንደዚህ አሯሩጠን የምናደርገው በትንንሽ ቪዲዮ በ30 በ40 ሰከንድ የምናደርገው ነገር ሳይሆን በደንብ መስማት፣ በደንብ ማስተዋል፣ ብዙ ማንበብ ይጠይቃል እና አይሆፕ ይሄ ቪዲዮ የተወሰኑትን ያግዛል ብዬ አምናለሁ። በትክክል መማር ለሚፈልጉ ሰዎች ለዚህ ነው መልእክቱን መጨረሻ ላይ ያደረኩት እና እንግዲህ ይጠቅማል ያላችሁ ሼር አድርጉት። የምንችለው ያህል እንደዚህ እያደረግን ይሄ ትውልድ እንዲማር ማናረግ ከሆነ ብዙ ጉዳይ ነው ያለብን እንደ ሀገር። እንደምታውቁት የፖለቲካና ማህበራዊ ችግሩ እንዳለ ሆኖ በእውቀትና በሳይንስ ወደኋላ የቀረ ነው። ደግሞ እስከ መቼ ድረስ ነው ሀገራችን የሌላ ሀገር እውቀት ተቀባይ የምትሆነው? የሌላ ሀገር እውቀት፣ የሌላ ሀገር ሳይንስ፣ የሌላ ሀገር ባለሙያ፣ የሌላ ሀገር መጽሐፍት፣ የሌላ ሀገር መድኃኒት፣ የሌላ ሀገር ቴክኖሎጂ እስከ መቼ ነው እኛ ተቀባይ ሆነን የምንሆነው የሚለውን እንድትጠይቁ ፈልጋለሁ። ይሄ ለኢትዮጵያውያን ነው። I'm very sure because this recording was done in English, so whoever is interested in research and research quality have the opportunity to get some lesson from this highly experienced, one of the best statisticians in United States, Professor Carl Galvin. He's almost graduating. I mean, he's retiring. I said graduating. He's retiring now. So it's a very big opportunity to have the chance to hear from his experiences. He's sharing based on his research for the last 30-40 years. So I am very lucky to be here, but I couldn't really share enough. I wish a lot of young people, a lot of researchers, a lot of the academic and research community, even people outside research, have the chance to hear at least some of these basic things about research quality. You don't have to do research, but in one way or another, our life is connected to evidences and research process because we are using results from science. All the medicine, all the foods we eat, all the materials we get are out of technology, out of science, out of research process. So it's just good to make the young people think in this direction. I know now with TikTok and all these short videos, it's not possible to catch attention of the young people and make them listen for 2 hours. That's not possible, but they should. We know we don't make everything very short. It's not possible. It's not about shortcut. This is about process. This is about just getting the basic things about how the science and the research community work. I hope you guys enjoyed, and I really thank Professor for his unreserved efforts for sharing knowledge. And all of us are part of the network, so we help each other by sharing, and so that these great messages reach those who want to get the knowledge. Thank you so much, and this is Fakadu from University of Nebraska, Lincoln, also working for Youth and Education Support Service. So thanks so much, and enjoy upcoming videos, also the other videos. I'm doing all my best to share and help in sharing, and I wish you nice time wherever you are. Thank you.